In this video, we'll be learning how to solve logarithmic equations that involve multiple logarithms. In our previous video on solving basic logarithmic equations, those equations contained just one logarithm, and we were able to get rid of the logarithm by exponentiating both sides of the equation. This time, when there are multiple logarithms in the equation, exponentiation won't necessarily get rid of all of the logarithms at once. Let's take a look at an example. In example A, we have the equation log with base 2 of x plus 3 plus log with base 2 of x minus 3 equals 4. So at first you might think, well, to get rid of the logarithms, we can perform the inverse operation, which is exponentiating with base 2. So we might do 2 to the power of the left-hand side and 2 to the power of the right-hand side. The problem is that this 2 to the power of the left-hand side isn't going to cancel out the logarithms. When you perform inverse operations, those operations need to be performed back to back in order for them to cancel out. For example, if we have x plus 3 and I want to get x by itself, then I can get rid of the plus 3 by immediately doing the inverse operation, which is to subtract 3 from this. Since the plus 3 and the minus 3 are done back to back, those operations will cancel each other out. However, if instead I have 5 times x plus 3, well, if I want to get rid of the plus 3 at this point, subtracting 3 isn't going to get rid of it. This is because the plus 3 and the minus 3 aren't being performed back to back. There's a multiplication by 5 in between. So again, inverse operations only cancel each other out if they're performed back to back. Now let's go back to our equation here and think about what's the last operation being performed on the left-hand side. For example, if we were to plug in some value in for x, and we try to evaluate that expression on the left-hand side, what order would we do the operations in? Well, we might do the x plus 3 first, then take its logarithm with base 2. Then we might do the x minus 3, take its logarithm with base 2, and then at the end, we would add the two quantities together. So the addition is the last operation being performed on that left-hand side. Which is why if we exponentiate with base 2, it's not going to cancel out those logarithms because there's an addition operation in between. What we're going to do is rewrite our equation so that logarithm is the last operation being performed on the left-hand side. And we can do that using the properties of logarithms. Remember that if we have the sum of two logarithms with the same base, then we can combine them together by multiplying what's inside. So we end up with log with base 2 of x plus 3 times x minus 3. And on the right-hand side, this is equal to 4. Now, if we think about the order in which we perform the operations on the left-hand side, we would first do the x plus 3, we would then do the x minus 3, we would multiply those two quantities together, and then lastly, we would take the logarithm with base 2. Since the logarithm is the last operation being performed on the left-hand side, now if we exponentiate both sides with base 2, that will cancel out the logarithm. So once those two operations cancel out, we're left with just x plus 3 times x minus 3 on the left-hand side, and on the right-hand side we have 2 to the power of 4. So we've transformed our logarithmic equation into an algebraic equation. And now we can solve this by multiplying out the x plus 3 times x minus 3. So multiplying the first terms, we get x squared. Multiplying the outer terms, we get minus 3x. Multiplying the inner terms, we get plus 3x, and then multiplying the last terms, we get a minus 9. And on the right-hand side, 2 to the power of 4 gives us 16. We notice here that the minus 3x and the plus 3x will cancel each other out. So if we want to solve for x, all we have to do is add 9 to both sides of this equation to get x squared equals 25. And then to isolate the x, we can take the square root of both sides. We get x equals plus or minus 5. Now, when we're solving these types of logarithmic equations, we have to be careful. The x values that we obtain may not actually work when we plug them back into the original equation. You came across a situation like this when you solved equations involving square roots in algebra. Just like for those types of equations, we'll need to check our answers by plugging them back into our original equation. The reason why we might have an issue is because we can't take the logarithm of every single number. Specifically, we can't take logarithms of numbers that are 0 and below. So let's check the answers that we found here. For example, let's start by checking x equals -5. Plug that back into your original equation. We would end up with log with base 2 of -5 plus 3 plus log with base 2 of -5 minus 3 equals 4. Simplifying this, we have log with base 2 of -2 plus log with base 2 of -8 equals 4. We see here that there's a -2 inside of a logarithm and -8 inside of the logarithm. Those are operations that we cannot perform. Because if you try to think about what is log with base 2 of -2, you're trying to think 2 to what power gives us -2. But 2 raised to any power is always positive. It's never 0 or below. So that's why we can't take the logarithms of numbers that are 0 or below. So we would say that the logarithm with base 2 of -2 and the logarithm with base 2 of -8 are invalid operations, which tells us that x equals -5 is not a valid solution. Let's now check our other solution. Let's check x equals 5 and plug that into our original equation. We would have log with base 2 of 5 plus 3 plus log with base 2 of 5 minus 3 equals 4. Simplifying the expressions inside the logarithms, we have log with base 2 of 8 plus log with base 2 of 2 equals 4. At this point, we don't need to go any further because these logarithms are valid operations to perform. And this also tells us that x equals 5 is a valid solution to our equation. So for our equation here, the only solution is x equals 5. Let's try another example. In example B, we have log with base 3 of 5x minus 4 equals 2 times log with base 3 of x. Once again, you might think that to cancel out the logarithms, we need to exponentiate both sides with base 3. So do 3 to the power of the left-hand side and 3 to the power of the right-hand side. If we do this, the logarithm on the left-hand side will cancel out with the exponentiation because those two operations are being performed back to back. However, the logarithm on the right-hand side will not be canceled out by this exponentiation. This is because the logarithm was not the last operation on the right-hand side. So when we exponentiate it with base 3, those two operations are not being performed back to back. There's a multiplication by 2 in between. So there's something we need to do before we exponentiate both sides with base 3. Remember that we had a log property that told us that if we have any multiples in front of the logarithm, we can bring them inside as exponents. So let's rewrite our equation. On the left-hand side, we still have log with base 3 of 5x minus 4. On the right-hand side, bringing that 2 in as an exponent, this gives us log with base 3 of x squared. Now, we see that the logarithm is the last operation being performed on both sides. So if we exponentiate now with base 3, that's going to cancel out both of the logarithms. And so our equation becomes 5x minus 4 is equal to x squared. We've now transformed our logarithmic equation into an algebraic equation. To solve this equation, what we'll do is move everything to one side and try to factor. So we'll subtract 5x from both sides, we'll add 4 to both sides. This leaves me with 0 on the left-hand side equals x squared minus 5x plus 4. To factor this polynomial on the right-hand side, we need two numbers that multiply to 4 and add up to -5. Those two numbers would be -1 and -4. So we have 0 equals, on the right-hand side, this factors as x minus 1 times x minus 4. And now what we can do is split this equation up into two parts. We have x minus 1 equals 0 and x minus 4 equals 0. On the left-hand side, we can add 1 to both sides to get x equals 1. On the right-hand side, we add 4 to both sides to get x equals 4. So these are my two potential solutions, x equals 1 and x equals 4. But we need to confirm whether or not they actually work in our original equation. So let's start by checking x equals 1. Plugging this into our original equation, we have log with base 3 of 5 times 1 minus 4 equals 2 times log with base 3 of 1. On the left-hand side, this simplifies to log with base 3 of 1, and on the right-hand side, we have 2 times log with base 3 of 1. So when we check these equations, all we really need to make sure is we can actually perform the logarithms. Looking inside the logarithms, we have 1 inside both of our logarithms, and that's something that we can compute. As long as we're taking a logarithm of a positive number, everything is okay. So in this case, these logarithms are valid operations, which tells us that x equals 1 is a valid solution. Let's now check our other solution, x equals 4. Plug that into your original equation. You have log with base 3 of 5 times 4 minus 4. And on the right-hand side, 2 times log with base 3 of 4. On the left, we have log with base 3 of 20 minus 4, which is 16. And on the right, we have 2 times log with base 3 of 4. Again, all we need to make sure is we can actually take these logarithms. And as long as the numbers inside the logarithms are positive, we're okay. In this case, both of those logarithms are valid operations, which tells me that x equals 4 is a valid solution. So for our equation here in example B, we have two solutions, x equals 1 and x equals 4. Let's work through a couple more of these examples. In example C, we have the equation log with base 3 of 4 minus 2 times log with base 3 of x is equal to 2. Let's try to solve this equation. Just like with the other examples, what we want to do is get rid of the logarithms by exponentiating. But we need to make sure that the logarithm on the left-hand side is the last operation being performed. That way it cancels out with the exponentiation. We'll start by combining our logarithms together using our log properties. So first of all, the 2 multiplied to our logarithm can be brought inside as an exponent. So we end up with log with base 3 of 4 minus log with base 3 of x squared equals 2. Now we can combine these two logarithms together. If we're subtracting logarithms, once we combine them, we'll divide what's inside. So we'll end up with log with base 3 of 4 divided by x squared equals 2. Now that the logarithm is the last operation being performed on the left-hand side, we can cancel it out by exponentiating both sides with base 3. So let's do 3 to the power of the left-hand side and 3 to the power of the right-hand side. Once again, the logarithm with base 3 cancels out with the exponentiation with base 3, leaving us with 4 over x squared on the left-hand side, and we'll have 3 squared on the right-hand side. Simplifying this, we have 4 over x squared equals 9. And we can solve this equation by first multiplying both sides by x squared. This gives us 4 equals 9x squared. And then if we divide both sides by 9, we have 4 ninths equals x squared. And then lastly, we can take the square root of both sides to isolate the x. We get x equals plus or minus 2/3. Lastly, we need to check whether these x values actually work in our original equation. Let's start by checking x equals negative 2/3. Plugging that into the original equation, we have log with base 3 of 4 minus 2 times log with base 3 of negative 2/3 equals 2. Now let's see if we can actually perform the operations in this equation. Specifically, can we do those logarithms? Our first logarithm is log with base 3 of 4. This is a valid operation because we can take the logarithm of a positive number like 4. On the other hand, for our second logarithm, we have log with base 3 of negative 2/3. This is not a valid operation because we can't take the logarithm of a negative number. Since we can't perform all of the operations in this equation, we would have to conclude that x equals negative 2/3 is not a valid solution. Now, let's check x equals positive 2/3. Plugging this into our original equation, we have log with base 3 of 4 minus 2 times log with base 3 of 2/3 equals 2. This time, both of the numbers that are inside the logarithms are positive. so they're both valid operations, which means that our answer, x equals 2/3, is a valid solution. So for our equation here, x equals 2/3 is our only solution. So now let's look at example D. Here we have log with base 6 of x plus 4 equals 1 minus log with base 6 of x plus 3. Our goal here is to combine the logarithms together, that way we can exponentiate both sides with base 6 to get rid of the logarithm. So in order to combine the logarithms, I might start by adding log with base 6 of x plus 3 to both sides of the equation. This gives us log with base 6 of x plus 4 plus log with base 6 of x plus 3 on the left-hand side, and on the right-hand side we'll just be left with 1. Now, if I have a sum of two logarithms, we can combine the logarithms together by multiplying their insides. So we have log with base 6 of the product of x plus 4 times x plus 3 equals 1. Now that the logarithm is the last operation on the left-hand side, we can undo that logarithm by exponentiating both sides with base 6, which means we're going to do 6 to the power of the left-hand side and 6 to the power of the right-hand side. The log with base 6 cancels out with the exponentiation with base 6, leaving us with x plus 4 times x plus 3 on the left-hand side and 6 to the first power on the right-hand side. Now to solve this resulting algebraic equation, what we'll do is we'll multiply out these polynomials using the FOIL method. Multiplying out the first terms, we get x squared. Multiplying the outer terms, we get a plus 3x. Multiplying the inner terms gives us 4x. And then multiplying the last terms, we get plus 12. On the right-hand side, 6 to the first power is just 6. Next, let's move everything to one side and try to factor this equation. We can subtract 6 from both sides. This leaves us with x squared. The plus 3x and the plus 4x combine to give us plus 7x. And then lastly, the positive 12 minus 6 gives us plus 6 and then equals 0. So if I want to factor that left-hand side, we need two numbers that multiply to 6 and add up to 7. Those two numbers would be 1 and 6. So our left-hand side here factors as x plus 1 times x plus 6, and this is equal to 0. When we have a product of two things and it equals 0, that tells us that either the first factor equals 0 or the second factor equals 0. So this allows us to split our equation up. We have x plus 1 equals 0 or x plus 6 equals 0. On the left here, if we subtract 1 from both sides, we end up with x equals negative 1. And on the right, if we subtract 6 from both sides, we end up with x equals negative 6. The last thing we need to do is check whether these x values here are actually solutions to our original equation. So let's plug them in. Let's start by checking x equals negative 1. Plugging that into our original equation, we have log with base 6 of negative 1 plus 4 equals 1 minus log with base 6 of negative 1 plus 3. This gives us log with base 6 of 3 on the left-hand side and 1 minus log with base 6 of 2 on the right-hand side. In both of these logarithms, we're taking the logarithm of a positive number, which means these are valid operations. So x equals negative 1 is a valid solution. Now let's check x equals negative 6. Plug that into our original equation. We end up with log with base 6 of negative 6 plus 4 equals 1 minus log with base 6 of negative 6 plus 3. On the left, we end up with log with base 6 of negative 2 equals 1 minus log with base 6 of negative 3. Looking at the logarithms that we have in our equation, we see that we're taking the logarithms of negative numbers. We can't take the logarithm of a negative number, so these are not valid operations, which means x equals negative 6 is not a valid solution. So for our equation in example D, the only solution is x equals negative 1. So in this video, we learned how to use our log properties to help us solve logarithmic equations that involve multiple logarithms.